Well, hello everyone. Today we're going to be talking about chemical bonds. And as you can see on the introduction screen, we have three different kinds of bonds we're going to be looking at today. Actually, there are four, but we're not going to talk about the metallic one just because we're going to get to that a little bit later. But if you take a look at the three that we're going to look at today, we're going to look at salt as a type of that has this type of bond. We have this methane molecule that represents another kind of bond, and of course, good old water right over here. It too has a different kind of a bond as well. So we're going to look at all three of them and see what the differences are, and also how to calculate or classify each one of them according to their bonds. So let's go ahead and get started. The first type of bond that I'd like to introduce to you is the ionic bond. The ionic bond, for the most part, I guess one word that would best kind of describe it is it likes to transfer its electrons. It's not going to keep them all in one place per se, and it's not really going to share them. It's going to move them around, and as it moves it around, it creates a situation like, for instance, the sodium is going to be a little bit more positive than the chlorine. That's going to be a little bit more negative. Because it transfers it back and forth, it's really not losing them, it's just kind of moving them around. So that's what an ionic bond is about. It's about transferring those electrons. The next kind of bond is going to be covalent bonds, and there are two different kinds of covalent bonds. Ones that share their electrons well and evenly, and those are called nonpolar. The nonpolar types in this situation will take all of those electrons and share them. That's kind of the key word for covalent bonds, is they're going to share them. And the nonpolar shares it evenly, so there's no pole. So there's no positive pole, there's no negative pole, kind of like a magnet. It shares it fairly easily. Now the other type is what we would call a polar type. And they share that unevenly. And in this particular case, what's going to happen is the electrons are going to be kind of more in one area than the other. And because of that, it creates poles, a positive and a negative pole. As a matter of fact, if you were to try to get these two to mix, like we put them in a container and shook them up and try to get them to mix, they wouldn't, because they have different bonds. And because of that, those differences are going to be seen, like we talked about trying to mix oil and water together. Well, the same kind of situation. The oil type is like this non-polar bonding versus the polar bonding. And for get these things to mix, they have to be of like bonds. So that's what a covalent bond is. It's about sharing some evenly, some unevenly. But before we go any further and to figure out how do we know if they're covalent or if they're ionic or they're nonpolar, is this rule called the Octet Rule. The Octet Rule is the concept of, on the outer shell of all of these elements, to be stable and happy, they have to have 8 electrons. It's kind of like trying to own some kind of kit or collection to have 8 of something. So for them to be happy, to be stable, they need to have 8. To give you kind of an idea of what I mean by that, if we take a look at this carbon dioxide molecule, you got 1, 2, 3, 4, 5, 6 electrons in an oxygen element. So it wants 2 more in the worst way. So the thing that kind of makes it happy is it has 1, 2 electrons from one half of the carbon molecule, and then on the other half we have 2 electrons, and then we're going to put our 4 electrons in the outer valence, or 6 electrons in the outer valence from the oxygen. So at the very end of the day, each one of these oxygens have 8 electrons. The carbon has 8 electrons. They're extremely happy. Now let's take a look at kind of the official definition of the Octet Rule. Atoms are most stable when the outer valence is filled with electrons, and in particular 8 of them. Except for hydrogen and helium, a filled layer contains 8 electrons, called an octet. Atoms do one of two things. They're either going to lose or gain or transfer those electrons, which mean ionic compounds, or they'll share electrons, which we term covalent. And electrons will either make a filled layer or they'll empty it so they can go to the next layer and fulfill the octet rule. So that's how that works. Now let's take a look at how we can use the periodic table to determine what kind of element that we're talking about. Now this you should, and while I'm talking I'm going to be pulling down some things, a scale if you will. But if you take a look at this, we have the Electronegativity Scale, and you should already know what electronegativity is. It's the desire or power of a particular element to draw in electrons. Each element is assigned this electronegativity, and it tells us how badly they want, if you will, an electron. To give you kind of an idea, and again, you've done this before, and as we travel from the alkali metals over here to the halogens, you know the electronegativity increases from 0.7 to just around 4. And then if you go down into the families from the top to the bottom, we actually get a decrease in electronegativity. So francium over here has an electronegativity of 0.7. Doesn't have a huge desire, primarily because it only has 1 electron. It would just as soon give that up so that it can go to the next level that it has 8. On the opposite spectrum over here, we have fluoride, I mean. It has electronegativity of 4. It has 7 electrons, and it only needs 1 more. If you've ever collected anything and you just need 1 more, you'd trade, you'd maybe pay a higher dollar for it. It has extreme desire to get 1 more electron in its outer valence so that it can be complete and much more stable. Well, with that in mind, we have a scale over here, and that scale essentially says if something is between 0 and 0.4, it would be considered a non-polar compound. If we have something like 0.4 to 0.7, what that would be a compound that tends to be more polar in nature. Anything above that, of course, would be ionic. So let's take a look at a couple of them. Let's first of all take a look at CO2 that we've already mentioned. Now if you go up here to carbon, that has electronegativity of 2.5. So you get 2.5. And we're going to subtract it from oxygen, which is a 3.5. So we have a number of 1, and this 1 will fit somewhere right in this region right in here. So it would be considered have a polar bond. Let's do one more. Let's say NH3. So we're going to do N, ammonia, H3. So we know that if we go up to hydrogen, it's 2.1. And we're going to subtract that from nitrogen, which is 3.0. That will give us a 0.9, which would put it right up here again in the polar division. Let's look at one more that we've seen, and that's salt. We're going to go Na, sodium, chlorine. And let's first of all go to chlorine. It has a large number, 3.0, for electronegativity. We're going to subtract it from sodium, which is over, oops, where we go here? Right there. That's at a 0.9. That will give us a 2.1 electronegativity, which falls on this side of the 1.7, so it would be ionic in nature. So that should give you a little bit of a feel of how you can classify them based on their formula. And we're going to be doing a few more of those in class, so I'll be seeing you then. And the thing you should always remember Remember, they're bonds. Chemical bonds. I'll see you later. Thanks. Bye.